everyone. Today we're going to go over how to linearize data or transform data so that we may perform a linear regression on the data. So, objectives. Number one, we are going to decide if the least squared regression line is the best fit for the data. If it's not, then we're going to linearize the data or transform the data so that it is linear. Number three, check if the transformed regression model is a better fit than the original regression. So that's basically statistical practice. Number four, use the transformed regression equation to predict future values. And number five, this is kind of a caveat or an extension of the project. We're going to use these values to propose a prediction for another value. So this is not really very statistical based here, but I'll get to that in a second. It's kind of reaching, but it's, just to estimate, right? We could just estimate. But before I get into the context of the problem, I'm going to show you what the data set looks like. We're going to start by importing the libraries that we need. So the first one would be pandas for data manipulation. We would want to do NumPy because we're going to need that for our calculations. We would want to do SciPy because we're also going to need that for our calculations. And then for plotting, we're going to do matplotlib.pyplot_splt, and we're going to do Seaborn as well. Okay, run that. So next thing is to create a data frame. So we're going to set a variable data frame, and we're going to set it equal to pd.dataframe. So what this is going to do is just going to create a data frame. So we're going to add a dictionary inside. And actually, let's see. I think I have the copy and pasted. So I'm going to paste this code in the description box below so that you may copy it. So I'm going to paste this code below so that you may copy it. We're going to go ahead and call that variable, and this is what the data frame looks like. So we have one column is the length of cavity of a left ventricle, and then we also have the heart weight. Okay, so now that you've seen the data frame, let me go explain what each of these columns mean, give you some context, and then also what the problem is and how we're going to solve it. Okay. So I just made this up like an hour ago, so bear with me. It is not perfect. There are some limitations. I wrote them down here. So I realized that there are things that we could have done better, but with given the data that we have, it's not the best, okay? But I did my best, and I came up with something that, extends the problem to a more real world issue, right? So I am a veterinarian, and I will be on maternity leave tomorrow. We have new animals coming into our shelter who will be staying with us for a certain amount of time. I want to be able to order any necessary treatments for possible problems in advance before I leave. So one major problem to consider is poor blood circulation. So how can I determine which animals will be more likely to have poor blood circulation? Well, this data set again has the length of the cavity of the left ventricle and the weight of the heart of the animals we already have. We can determine if the new animals will be more likely to have poor blood circulation if the weight of the heart is smaller, because smaller hearts may lead to less blood circulation. A smaller heart is not the most popular or occurring reason for poor blood circulation, but it is possible for it to be a reason why your blood circulation is low, or not but an animal's blood circulation is low. So that's why we're going to be using that, right? So my thing is, like, think of a giraffe. So it's a big animal with a bigger heart with a long neck because it needs to pump harder. With a bigger heart because it needs to pump harder in order to get that blood to the brain, which is 6 feet from the heart because it has a long neck, right? So if it were to have a smaller heart, it may have less blood circulation, right? So that's the thing. So we want to so the goal is there are going to be 5 new animals coming to the shelter while I'm gone, and the only thing that I have from them is the length of the cavity of the left ventricle, right? So I'm going to get into the anatomy real quick so you know what that is, but those are the only measurements I have. But luckily for me, I have a data set where I can predict from the left from the length of the cavity of the left ventricle, I can predict the heart weight, so how much the heart weighs, right? So if I do that, by knowing how much the heart weighs, I can compare, okay, well, which one would be smaller, and then which one would be fine, right? So a normal heart size, right? So those who have a smaller heart size, and we're going to define that as an animal who has a heart weight less than the heart weight of the average animal, so the average heart weight. If anyone who has less than the average heart weight is going to have poor blood circulation. That's what we're going to say. And note that yes, we could have if we had an ideal data set where all the animals were the same species, so let's say like dogs, and we could have just looked at the distribution and see if there were any outliers. So what minimum value would the heart weight, could the heart weight be before it's considered abnormal? And we could have just conditioned the data set to see, okay, any values less than this this value would be considered abnormal, so therefore it would be considered smaller, right? More specifically, outliers, that are less than Q1 minus 1.5 IQR, because that's what, the minimum value of the heart weight before it's considered an outlier to the left, right? And we also have to the right, but we want to focus on the left because we want to talk about way too small. So any values that are less than that value, that means, or any heart weights that are less than that heart weight means that they're too small. So then we would have been like, okay, these are too small, so that means that these would be the animals who would have, are more likely to have poor blood circulation. But in this case, we don't have the same species for the data set. These are just random animals, so we can't do that. So for the sake of the data set, we're just going to just take the average heart weight, and then anything less than that would be abnormal, okay? So these are the length of the cavity of the left ventricle. So that's where we're going to go with. So what is a cavity, first of all? So a cavity is a fluid-filled space inside the body that holds and protects internal organs. So if you take a look right here at this picture, the heart is actually in what's called a pericardial cavity. So that's this blue border you see here. So that's the heart's cavity where it's in, right? So you can think of it as a sac. So it's like holding basically all the organs. And cavities can be divided into subcavities. So in the heart, right, you have 4 different types of cavities, and they are the left atrium, the right atrium, and the left and right ventricle. So this is the right atrium, this is the left atrium, the left ventricle, right ventricle. You can consider these subcavities, right, because they hold whatever's in here. So what we want to measure is actually the size of the left ventricle. So basically this blue border here, this is what we want to measure. We want to measure the length of the left ventricle of each animal. So that's what this data is telling us. So for example, animal number 1, in this case, you know how Python starts with 0. So animal number 1 has a length of 0.55 centimeters for its left ventricle, and then its heart weight is actually 0.13 grams. Okay, so that's what we're doing. We're measuring the left ventricle, and then we're seeing, okay, it has a relationship with the heart weight, and we're going to use that relationship to predict the heart weight for these animals here that were given their measurements already, and then we're going to see based on the results at the end, okay, just by eyeballing it, this is basically what I was saying in part 5. We're going to use these values to propose a prediction for another value. So in this case, we're going to use the predicted heart weights, right? The predicted heart weights to propose a prediction if these animals are going to have a poor blood circulation or not. Okay, so that's number 5. So that's the context of it. Let's get started with the code. Okay, so after you run in the data frame, we're going to plot the relationship between the length of the cavity of the left ventricle and the heart weight. So again, when you have 2 quantitative numbers and you want to plot a relationship between them, you want to use a scatter plot. So we're going to use Seaborn to do that. So we're going to do seaborn.scatterplot. and we're going to set our x equal to, obviously, our x values, so that's going to be the length of cavity of left ventricle, and we're going to set our y equal to our y value, or in other words, our dependent variable. Okay, so basically, again, explanatory variable is this one, dependent variable is this one. So this variable, the length of cavity of the left ventricle, explains the heart rate. Okay, so let's do that. Okay, make sure we don't have two brackets there. What's wrong now? Let's see if we can fix that. Oh, that's why, because we moved it so that's okay. Got that. Perfect. So this is the relationship. This describes the relationship between the length of the cavity and the left ventricle and the heart rate. So I'm actually going to, I'm going to use Matplotlib to give it a title. Okay, so now you can see it there. So this is nice, right? So we have a relationship and you have a scatter plot. You can see the relationship between the x variable and the y variable, right? So now notice something. If this relationship was linear, we could definitely just from the get-go just get the linear regression, apply it, and then plug in our x and then get our predicted value. But notice that this is actually a strong, positive, non-linear relationship, okay? This is a strong, positive, non-linear, oh please. Strong, I can't even speak, oh, I can't even type either. Strong, positive, non-linear relationship. So because it's non-linear, we can't apply the least squared regression line, right? Because it's supposed to be linear. So the question is, can we perform a linear regression on this data? Why or why not? No, because it's a non-linear relationship. No, because it's non-linear. That's the key. It is not linear. Okay, no, because it's non-linear. So another way, actually, we can, why is this here 2 times? Okay, sorry, this is supposed to actually be, let me delete that, or no, let me just copy and paste it again. Just know that this is supposed to be here too. Okay, so we plotted the data already. We're also going to check the R-squared value, so this is the coefficient of determination. So what this value tells you, it explains the variability of x in the linear regression. So let me actually give you a better definition. So basically, R squared is the percent variation in y explained by the least squared regression line. So with x. So in other words, it explains the variability in the heart rate by the regression line that we use with x, okay? So it's basically talking about how much variability there is in the heart rate using that linear regression. And the more variability that the regression explains, the better fit it is for the data. So we're just going to find the value now, and then once we go further on, we're going to come back to this and we're going to compare models. So the way we do this is we just take the df.core method, and it should give us a R value. So what this is actually just our R value. It is our correlation coefficient, but all we have to do is take that value and raise it to the second power, right? And that's going to be our R squared. Okay, and if we want to actually find what our R squared is, we can just run it. And so that is our R squared. So in other words, 89.37% variation in heart rate explained by the least squared regression line with the length of cavity of left ventricle. Okay, so that's what the R squared means. Now we're going to check the residual plot. So the residual plot basically is, the residual is actually the difference between the actual value, so the actual heart rate in this case, minus the predicted, predicted heart rate, right? So we're going to check the residual plot, and so then we're going to analyze. I'm going to show you how to analyze the residual plot. So to do this, we're going to use SNS. We're going to use the resid plot function. We're going to do the same thing. So data frame length, oops, that's not what I meant. And then y, data frame heart. Okay, let's plot that. All right. So now, if you take a look at the residual plot, you can see that it's a curved pattern. So here is a rule to keep in mind. If there is a pattern, it means that it's not the best fit, okay? So because there's a pattern, that means that this a linear regression is not the best fit. So that's another way of knowing if we can perform a linear regression on this data. Well, no, because you can see that the residual, so the differences between the actual and the actual heart rate and the predicted heart rate is has actually a pattern. Okay, so not the best fit. So if not, how can we do something similar? Well, the answer is by linearizing the data or transforming the data. So we're going to linearize the data. So we're going to use a power regression, not a power regression. We're going to use a power model. So the way we're going to do this is we're going to set something up here. So we're going to use np.log10. And all we're going to do is we're going to take the data frame of the heart rate. We're going to run that. And we're going to set that equal to, let's call it log x. So what does this mean? This means that we are taking the log of x, right? So now, actually, hold on. I'm going to actually make it a column so that we can see it. And I'm going to do the same thing for y. I'm going to call it log y. And I'm pretty sure, oops, messed up a little bit here. This is actually supposed to be our x, right? So length. And then this is supposed to be, okay. So now if we run our data frame, it's actually going to show two new columns, so log x and log y. So why did we do this? Because when we're using a power model, the change that we're making in our equation is that we're taking the log of both variables. So that's what a power model is. That's how we linearize the data. So instead of using the normal x and the normal y, we're now going to be using log x and log y to linearize our data. So we're going to see if this model is a better fit for the data than the original linear regression. Okay, so the way we're going to do that is by plotting the transformed data. So we're going to go ahead and do SNS again. We're going to do a scatter plot again. Let's have our x instead. This time we're going to say log x. And our y, we're going to say data frame log y. Okay, we're going to run that. And now you can clearly see the difference. Now the data is linearized, right? So you can see the difference between this data set, this graph, right? The data was curved, right? And this what am I saying? This graph. Now you can see that it's linearized. Now we can apply a least squared regression line because the data is linear, okay? So we're also going to check the R-squared value. So we're going to do df.core. So we're going to check the relationship between log x and log y now, and that is this number right here. So we're going to take R-squared. We're gonna set that, square it, and then we're gonna do r squared, run that. And now we see that this is the coefficient of determination. So this is, so what is it? 99.33% of the heart rate variation is explained by this equation. While if we go back here, only 89.37% of the variation of the heart rate was explained by the by the least squared regression line in terms of the length of cavity of the left ventricle. So which one would you say is better? The one that explains 89% of the variation, or the one that explains 99% of the variation? I would say this one is a better model, because not only can you visually see that it's more linear than the first graph, but also it has a bigger or greater coefficient of determination. That's what the r squared is called. Okay. We're also going to check the residual plot. This is another way, right? So we're going to do SNS dot resid plot, set x equal to data frame log x, and we're going to set data frame log y. Okay, run that. What do we do now? Oops, it's capital X, isn't it? Okay, run that. Now, if you compare the difference between this graph and what is it? Where is it? This graph, actually, I'm going to do you a favor to make this easier for you, and I'm going to plot it in the same figure so that you can just compare. So I'm going to do comparison of resid plots or residual plots of such abbreviations. So I'm going to do plt.figure. You can just ignore this for now. This is just so you can visualize this. So here is, why did it not show up? Oh, could I put it here? Okay, the title didn't show up. Okay, perfect. So here's the comparison, right? So which one would we say has a better, is a better fit? Well, the one that doesn't have a pattern. This one obviously has a curved pattern. This one has its residuals random. So its residuals are random. They're not placed in any sort of pattern. So not only do we have a greater coefficient of determination, we have no pattern in the residual plot, and in the graph itself of the data, we can see that it's so much more linear than the first graph right here. And I'm actually going to do you a favor once more, and I'm actually going to do the same thing. So comparison of models. Okay, we're just going to leave it like that. Comparison of models. I'm just going to copy the code that I have right here. People say not to copy code because you might like mess up or something, but I'm just like, whatever. I mean, not a big deal, is it? Probably is if you're working on big projects. Okay, so, okay, so delete this. Move it here. Delete that. Move that. And then what else? Delete this. And I'm pretty sure this is the length, right? And now we want, what do we want? We want this one, right? Okay. And this is the power model, right? I was going to say this is the original model. Okay, So clearly, the original model had a curved, well, not a, well, we can say non-linear relationship, while the power model has a linear relationship. So now we can apply that least squared regression line to the power model, right? Because it's linear, right? So let me fix one more thing because I don't want to get you confused. So original model residual plot, that's what we're actually plotting here, and then power model residual plot. Okay, run that once more. So yeah, so those are basically our conclusions. So if I said that this is a better fit, then we can use the linear regression equation for this model to predict the heart rate of the new animals. So first things first is use a transformed regression equation to predict the heart rates of these 5 new animals. Well, where do we get the transformed regression equation? Well, first of all, if you have a calculator, you could do it that way. Or if you want to use pandas, we can use pandas. So I'm actually going to go here, make a new section. I'm going to say find equation. Okay, and the way we're going to do this is by using SciPy. So we're going to do SciPy, so sc dot stats, and we're going to use this linregress function, and we're going to set our x equal to data frame. What is our x? Okay, our log x, and then we're going to have our y equal to our log y. Now, if we run that, what this is giving us, it's giving us the slope, the intercept, and that's pretty much literally all we need right now. We don't even need to look at anything else. But the slope and the intercept to use our equation. So what I'm going to do is I'm going to write the equation here. Just give me 1 second. Okay, so we're going to say the predicted what heart rate is equal to our intercept, right? Why did I copy like that? Our intercept plus our slope, right, times the length of the cavity, the length of cavity of the left ventricle, okay? That is what our linear regression equation is supposed to look like, because again, so let's do hat y. I'm going to say just, I can't even say hat y. Predicted y is equal to a plus bx. Okay, that's our normal linear regression equation. But in a power regression equation, it's actually not a power regression equation, but what we want to do is we realize that we linearized a power function. So in order to actually get our actual answer, we need to make it so that it's going to give us our answer if it were to just be like a power regression. So the way we do that is by by multiplying both values, both independent and dependent variables, by log. So that's predicted y equal to a plus b times the log of x. Okay, and now that is our actual equation. So I'm going to go ahead and copy and paste that. So our real equation is actually the log of the predicted heart rate, right, times the log of the length of cavity of the left ventricle. So this is our actual equation. Now we're going to use that equation and we're going to see if we can predict certain values, right? So we're going to actually write the equation. So give me 1 second. So now the way we're going to do this is a little different. So we can't do like log of y equal to that. Like this is not math way. Like we can't just insert like an equation and then have them solve it for us. We actually have to think on our toes here. So what we can do is we can think, okay, well, I need to cancel out those logs, right? So how am I going to do that? Well, the way to cancel out a log, a dog, was I say dog? The way to cancel out a log is by raising it to the 10th power. So when we do that, right, we're just going to have y, right, our predicted y, and then we're going to have everything else raised to the, not raised to 10th power, raised to everything else. So that's going to end up being our actual equation. I'm just going to go ahead and get that from here, right, times this. And our first prediction that we want to make is an animal of 6.8 centimeters. So I'm going to plug that in right here. And because, again, this is not math way, we're not using parentheses for multiplication. We're actually using an asterisk. And also, the log function is actually from NumPy. So we're going to do NumPy.log, and we're going to make sure it says 10 because we want to get the base of 10, not the base of e. And why is that parenthesis there? Okay. Sure, we are good, I think. So we have 2 parentheses here. We have 1. I think we have 1 extra parenthesis. I think that should be enough. So when we run this, what is wrong now? Let's see. Oh. Forgot to add a multiplication sign in between again because it's not. Okay, let's see. np.log 10, because it's a function, we actually need to have it inside, right? Makes sense. Okay, I think we finally fixed it. So basically what we did is we canceled out the log from the y by raising it to the 10th power. Then we did the same thing on the other side. So for this side, we actually can show that we're raising it to the 10th power. We plugged in our thing in here, and we use np.log 10 to get the log of 6.8. So in this case, we didn't cancel out the log on this side, okay? And when we do that, and we get y, we get 299.6445. And what does this mean? This means that the predicted heart weight of an animal left with the length of 6.8 centimeters of their left cavity in their left ventricle is 299 point, let's say 299.65 grams, okay? So let me actually write that down because it's a whole mouthful. So the predicted heart weight of an animal with a 6.8 centimeter long left ventricle is 299 point, let's say 64.55 grams of 4 places, okay? So that is your answer. So let's continue on. So I'm just going to go ahead and copy and paste this, right, a few more times. So the next one is 2.3 centimeters. Let's do 2.3 on that. Okay, so what does this mean? This means that the predicted heart rate of an animal with what, 2.3 centimeters is let's see, it's 9.9764 grams. Okay, now moving on to the next one. So the next one is 9.6 grams. Predict that. So this one, wow. We can say that the predicted heart rate of an animal with a, 9.6 centimeter long left ventricle is 884.4273 grams. And finally, I think, do we have another one? Oh, we have two more. So 9 centimeters. We're going to do 9.0. Copy this. So the predicted heart rate of an animal with a 9 centimeter long left, a 9 centimeter long left ventricle is 722.2524 grams. And finally, we have 1.2. So the predicted heart rate of an animal with a 1.2 centimeter long, did I not copy this? 1.2 centimeter long left ventricle. Why did I put that? Okay. The predicted heart rate of an animal with a 1.2 centimeter long left ventricle is 700. Did I write this wrong? 1.2. Did that wrong. Okay. Is 1.294.7 grams. Okay. So now we have our answers. Perfect. So finally, the last part is predict which of those animals will be more likely to have poor blood circulation. So for our case, right, for our situation, we are going to define a small heart as an animal who has a heart rate less than the heart rate of the average animal. So first, we're obviously going to have to find, why is this here? I don't know if that's there. We're going to actually find the average heart rate of an animal. So we're going to do data frame, we're going to target the heart rate, and we're going to do dot mean. And so now we can say, okay, the average heart rate of an animal is 892.65, 29, right? 29 grams. Okay, so any number that's less than that, we can actually look at these numbers. We can say has a small heart. So is the first animal of 6.8 centimeters less than 892, we're just going to say 892 grams? Yes. So we're going to say yes for that. The second one also is yes. Third one is yes. Fourth one is yes. Fifth one is actually yes also. So our conclusion is that all of these animals, I'm going to be specific, all of the 5 animals have small hearts and are more likely to have, wow, I really can't spell, poor blood circulation. Therefore, I need to buy 5 treatments. I need to buy 5 treatments so that they may be treated, so that if this is true, or if they do develop poor blood circulation. Poor blood circulation, the treatment will be there, right? Treatment will be there, or be ready, right? And I don't have to worry about it while I am on maternity leave, right? So let's just pretend people call me no matter what, like if I'm on vacation, and I always have to fix the issues. So basically I don't have to worry about it if they do call me because the treatments are already there. So that is our wow, I really can't speak today. That is our conclusion I actually want to explore a little bit, so you can stop watching the video now, but I'm gonna add a few things. Let's see, so greater. So let's see, as we get greater, let's do 10 centimeters, maybe, no, let's do 12, and see if we get a heart weight that's greater than the average. So let's do 12, okay? Right, so perfect. So this animal right here, right, would be a very, very big animal, right? So it's actually greater than the average heart rate of an average animal that comes to the shelter. So we would say that if it were to be out of 6, we would say only 5 out of 6 animals are more likely um, to develop poor blood circulation. So we only have to really order 5 treatments instead of 6 treatments if this was like the 6th one, okay? So that would be a better example. Also, I wanted to show you that you can actually plot the linear regression. I'm actually going to do it right here for you. Not this one. Right here. So you can actually plot the linear regression for both of these. So I'm going to copy that. I'm going to go all the way to the bottom. And say plot the linear regression line, or in other words, the LSRL, so the least squared regression line. Least squared regression. I just realized I've been saying linear regression line. It's not linear regression line, it's least squared regression line, and you can only apply it on a linear function. Sorry, wow. Least squared regression line. Okay, so let's copy and paste that. Should look like this. Now, the way we're going to fix this, or not fix it, but the way we're going to add the linear regression is by actually using the regplot function. Okay, and what that's going to do is actually going to show you the data, and it's also going to show you, nope, that's not what I meant. It's also going to show you the linear line, the line that we're using to predict it. Okay, what did I do wrong? Oops, why did I do that? I meant to change it here, red plot. No wonder it was like giving me something weird. So what is it, the title? Okay. Run that. So here you can actually see, this is the original model, right? And you have this linear regression, and you can see that it's like literally not representing the data at all. And while this one represents the data so much better. So you can see, right, that the, what do you call it? The data points are very close to the line. And so basically what this is, it's going to actually predict the heart, the what do you call it, the heart weight, right? So the line is basically the predictions that we're going to get, and they're very close to the actual data points, while here they're not close at all. So that's another representation of like how we're not going to use this data as it is, and why we need to transform it in order to get a better linear regression. Let me see if there's anything else I want to add. I think I went over residual plots. Yes, of course I did. Let's think. Like anything different. I think that's it. There is one more method to transform data. So the way I did it, let's see. I just created a new data frame, right? We just created a new data frame. Where is it? Okay, right here. So what I did, I just created the data frame, but there is another way to transform the data more computationally. Like all I did was just do like np.log10 and then passed in all the values. What we could have done is use the dot transform method from pandas. And I'm going to link, I'm actually going to do that in another video because this is too long. So you can watch that video to see how to do that. And yeah, that's pretty much it. I hope you understand. If there are any questions, let me know. And if I messed up somehow, also let me know. But I just wanted to like say for credibility, this is an actual, the data, the source of the data I'm going to post on the description box, and this is actually, what do you call it? Where is it? Let me scroll all the way down. These values are actually accurate because this data is actually in my textbook, and I'm going to show you really quickly. The answer key. So for the first one, for the first centimeter, it was actually a problem in my textbook, and I'm going to show you what the answer key says. I just extended it to be like really extra. Okay, here. Not, okay, right there. So this is actually what the textbook says. So there's a strong positive correlationship between heart rate and length of left ventricle for mammals, because the relationship between the natural log of weight and the natural log of length is roughly linear. Heart rate and length seem to follow a power model. An exponential model would not be appropriate because the relationship between the natural log of weight and the length is clearly curved. And so for part C, they asked us to predict the weight of an animal who has a 6.8 centimeter long left ventricle, and that answer ended up being 299.77 grams. So where is it? Right here, so 299, it's pretty close, right? 299.60, what? 64%? 64%, please. 64 grams, but we got the whole number. So that's for credibility, just in case you're wondering, did she really do this like correctly? Well, yeah. So, and then so this should be a good prediction. So basically that was basically the problem, and then I just took that problem and then I invented like my own context to be like more real world or whatever. So there are some faults. Again, read the limitations. I'm going to post this code on the description box below also. Okay, anyway, that's it. Have a great day. Hope you enjoyed. Literally let me know if there are any comments or anything I could do better, or any concerns, or if I messed up by saying something that I shouldn't have said that's like statistically wrong, or anything. I'm open to corrections because your girl's a high school student trying to pass AP stats, so let me know. Anyway, have a great day. Bye.